Assalamualaikum and good morning to everyone. So my name is Muhammad Shakib Yusri and I'm from University Tenaga Nasional. Today I will be presenting my research entitled Characterization of Discrete Wavelet Transform DWT as Denoising Method for Phase or TDR signals. So before I begin, let me brief first the distributed acoustic sensing using phase or TDR technique and why it is chosen for our research. First, the phase or TDR technique allows simultaneous acquisition of strain or acoustic signals for the entire length of the fiber, where the fiber can be regarded as thousands of microphones installed, which can detect vibration, plus we're able to capture the acoustic energy along the optical fiber. So this system can be used to detect, locate, and extract the intrusion activities. So this based on phase or TDR has been explored in various applications such as perimeter protection, pipeline supervision, localization of protective fencing, airport protection, train monitoring, and border security. However, the overall phase or TDR system can be heavily affected by noises. So these noises can be originated from two sources. The first source can be from the surrounding environment. The second source can be from the configuration setup that include laser phase noise, stochastic nature of the relic backscattering, laser frequency drift, thermal noise in electrical and optical component, and finite efficiency ratio of the optical modulator. So these noises can contribute to low visibility that produces unreliable vibration measurement of the actual vibration activity detected. So other researchers also have explored wavelet transform to denoise the signals. However, a detailed methodology on the selection process of the mother wavelet, the level of decomposition, and the threshold was not discussed in detail. So let me begin the methodology by explaining the experimental setup. So experimental setup started with the continuous light source was being modulated into sequence of pulses by acoustic optic modulator before going through the signal amplification by the first EDFA. Then the amplified pulses are gated into the fiber under test. Next, the written relic backscatter signals passes to second amplification by the EDFA and going through a band pass filter to remove the ASE from the EDFA. So the optical signals then are converted by balanced photodetector and captured by the oscilloscope. So the relic backscatter signals at the receiver end represent the coherent interference of the relic backscatter signals at different points along with the fiber within a single pulse. So these traces will maintain a predictable and fixed shape until an intrusion induces a phase shift at the location compared to stable state trace. And figure 2 shows the 5000 superimproved relic traces coming from 0.1 second data. So data were then reconstructed in the form of two-dimensional array with m equals to the number of traces and n equals to the sampling point as shown in figure 3. Next, how does discrete wavelet transform work? So DWT decomposes the signals using a pair of complementary filters and downsamplers to eliminate unnecessary samples. So the DWT perform a correlation analysis where the output is expected to be maximal when the input signal most resemble the mother wavelet. And how does the denoising works? So first, DWT denoise the signal through Gaussian distributed approach by removing the noises that overlap with the relic signals. This is done by recovering the signals of interest from the original signal. And however, for the case of phase or TDR system, the noises are neither defined or known. Thus, the purpose of this denoising is to remove the noise with minimum error. Next, I will explain the algorithm to process the signals. The first step involves data collection and reconstruction of the signals obtained from the configuration setup. Next step involves the processing the raw data by applying normalized diversion method to localize the vibration events. Then, using denoise function in the MATLAB, we select the mother wavelet and decomposition level. And the next step involves selection of denoising threshold and threshold rules to the wavelet coefficient. And last step involves the reconstruction of clean signals through inverse DWT. And to study the effectiveness of different mother wavelet and decomposition level, a few combinations of them were chosen. And for this research, simulate Haar, Da Vinci, bioorthogonal, coafflate, discrete opposition of Meyer wavelet, Fever-Karuskin, and reverse bioorthogonal were chosen to be studied. And for the level of decomposition, level 3, 5, 7, and 9 were chosen. And for denoising threshold selection, 4 denoising thresholds selected that include empirical bias, minimax, sure, and universal threshold with soft threshold rule were studied. And to evaluate our system, we compute the SNR to determine how precisely the combination can eliminate noise while retaining as much as possible from the original signal. Next, I will discuss the results from the the results obtained. So denoising the phase OTR system plays an important role in pre-processing step before analyzing the acoustic signal detected by the system. So any noises that interrupt the data acquisition will result in false alarm, thus reducing the efficiency of the detection system. And in this study, we studied extensively the effectiveness of this wavelet method. From the table 1, level composition 3 shows the best results in performance parameter, where it has the highest SNR value compared to other level of decomposition. And in fact, the SNR slightly deteriorate at a higher decomposition level of the function, while for the mother wavelet chosen, simulate 4, WT4, and bioorthogonal 4.4 wavelet function show exceptionally better results compared to others, with an average of 13.8481. However, the SNR value for WT4 was slightly better than others, which is at 13.8808. And it should be noted that the denoising threshold and threshold rule was in default mode, which means that the empirical bias with soft threshold holding were being used. Following that, the influence of various denoising thresholds were then examined. So the soft threshold rule was chosen here to preserve the signal original structure, ensuring that the denoised signals retain all of its information. And 4 denoising thresholds indicated in table 2 were examined, which is the empirical bias, universal threshold, stain unbiased risk estimation sure, and minimax. From this table 2, the sure threshold technique employing the soft threshold rule performed the best, achieving highest SNR, which is at 15.5031 in comparison to other methods. And the best wavelet transformation results were obtained by combining the WT4 wavelet function with level 3 decomposition and sure threshold technique with soft threshold rule. And figure 5 shows the denoising signals with different denoising threshold using the soft threshold rule. And from the denoised signal obtained, using sure threshold with soft threshold rule removes noises from the original signals while preserving as much as possible the original signal structure, obtaining the highest SNR value compared to others. Thus, through this study, the WT4 wavelet with level 3 of decomposition using sure threshold, employing soft threshold rule produces the best result in terms of the SNR calculated. For the conclusion, this paper presented an approach for determining the optimal combination by underlying the mother wavelet, the level of decomposition, and the thresholding method for phased OTDR data. So SNR was calculated and used to compare the performance of each parameter. And the initial findings demonstrate that the level of decomposition increased, the SNR dropped, which is not ideal for the denoising performance. And decomposition at level 3 yields the best result regardless of the mother wavelet, while simulate 4, WG4, and coafflate 3, and bioorthogonal 4.4 all perform excellently. However, WG4 performed the best, obtaining the highest SNR, making it the ideal mother wavelet for our signals. Then we compare the denoising threshold, which conclude that sure threshold with soft threshold rule perform the best, achieving the highest SNR. And from this research, we can conclude that having a unique combination of thresholds and wavelet is critical in removing noises from our system. And this result provides the best wavelet transform selection for our system, which we'll then use in the next phase of our project. Next, I would like to thank Unit10 R&D for supporting our work for this research. And that's all from me. Thank you.